Welcome to Space Science. A solar storm has struck Earth and the auroras are suddenly surging across the sky. But why do these glowing waves appear so fast? And why do they sometimes spread far beyond the poles? In this video, we'll break down the science behind this stunning phenomenon and reveal what really happens when a solar storm collides with Earth's magnetic field. If you enjoy space documentaries and cosmic mysteries, like this video, subscribe to Space Science and join us for the journey. Far above Earth, beyond weather, beyond clouds, beyond the slow turning of seasons, the sun holds the widest setting for changes in auroral activity. It does not shine in a perfectly unchanging way. Its light seems steady to ordinary human life, and its daily presence suggests permanence. But the sun passes through a long magnetic rhythm that quietly alters the conditions of near-Earth space. This rhythm is called the solar cycle. A cycle, in simple terms, is a repeating pattern that rises, reaches a period of greater activity, and then settles again. In the case of the sun, this pattern unfolds over about 11 years in its visible activity, while the deeper magnetic pattern completes a full reversal and return over about 22 years. What matters at the widest level is that the sun is not constant in its outward behavior. It moves through calmer years and more disturbed years, and Earth remains inside that larger solar environment at all times. During quieter phases, the sun's visible face usually shows fewer dark sunspots, fewer large magnetic disturbances, and fewer major eruptions. During more active phases, sunspots become more numerous, magnetic complexity increases, and strong bursts from the sun become more common. This long waxing and waning does not create an aurora by itself in any single moment, but it changes the background likelihood that Earth will encounter more intense disturbances from the sun. In that sense, the solar cycle acts like a broad climate of activity for the whole inner solar system. It does not decide every event in detail, yet it sets the general conditions under which those events become more or less frequent. A year near solar minimum tends to be quieter in space weather. A year near solar maximum tends to be more crowded with powerful magnetic unrest. This wider rhythm begins deep within the sun, where hot charged gas moves in great flowing layers, and where rotation does not proceed evenly from one latitude to another. The sun is not a solid world. Its equatorial regions turn faster than its higher latitudes, and this uneven turning stretches and twists magnetic fields over time. The result is a slow rebuilding of magnetic stress on a vast scale. That stress rises toward years of greater surface activity, then reorganizes, weakens, and builds again in the next cycle. The visible signs of this process come and go, but the process itself never truly stops. Even in a quiet year, the sun remains magnetically alive. A quieter phase means reduced disturbance, not true stillness. From Earth, this long solar breathing is not obvious in daily life. Daylight arrives with familiar brightness. The sun still rises, crosses the sky, and sets. The eye cannot detect from ordinary sunlight whether the broader cycle is climbing or descending. Only careful observation over time reveals the pattern. Astronomers track the number and arrangement of sunspots, measure changes in the sun's magnetic field, and watch the changing frequency of solar outbursts. Through this patient record, the sun ceases to look like a fixed lamp and begins to appear as a star with moods governed by physics rather than chance. The cycle is not perfectly regular in every detail. One maximum can be stronger than another. One minimum can be deeper or shallower. The timing also shifts somewhat from cycle to cycle. Still, the overall pattern remains one of the clearest long rhythms in solar behavior. Earth lives entirely within the reach of that rhythm. The planet does not orbit beside the Sun in isolation from its changing magnetism. It moves through the extended atmosphere of the star, immersed in a continuous outward flow of particles and magnetic field called the solar wind. When the Sun is in a more active phase, this surrounding environment becomes more likely to carry stronger disturbances across interplanetary space. That is why a surge in auroral activity is not merely a local event above one region of Earth. It belongs first to a changing solar backdrop that spans millions of kilometers and unfolds over years. Before any visible brightening in the night sky, the wider solar setting has already been shaping the conditions in which such changes become more likely. The solar cycle also carries a quieter symmetry between appearance and consequence. To the eye, a more active Sun may still look almost unchanged, unless one observes it with proper instruments and safe methods. Yet the hidden magnetic condition of the star can differ greatly from one phase of the cycle to another. A calm-looking daylight Sun can belong to a year of high magnetic tension. A familiar disk of light can stand above Earth, while the greater space environment grows more unsettled. This separation between appearance and condition gives the solar cycle much of its power as an idea. It reminds astronomy that important changes do not always announce themselves through obvious brightness. Sometimes they appear first in counts, measurements, and long records rather than in spectacle. There is also no sharp wall between quiet and active years. The cycle rises and falls gradually. Activity clusters, then eases, then returns in altered form. Different regions of the Sun contribute unevenly at different times. The northern and southern solar hemispheres do not always behave in perfect synchrony. Peaks can broaden across many months. Strong events can still occur outside the most active period, though they tend to be less common. Observations indicate this general pattern with confidence, while some details of why one cycle differs from another remain under study. The Sun obeys magnetic laws that are understood in broad outline, but the exact strength and timing of each cycle are not known with complete precision far in advance. So at the widest outer level of this subject, the changing aurora begins with the long pulse of the star that Earth orbits. The Sun sets the larger condition. It provides the energy source, the magnetic environment, and the slow alternation between quieter years and more disturbed ones. This first region remains broad, patient, and planetary in scale. It is enough to see Earth moving inside the reach of a star whose calm light hides a recurring cycle of unrest. On the visible face of the Sun, the broad rhythm of the solar cycle gathers itself into more concentrated forms. These are active regions, the magnetically disturbed parts of the solar surface, where the Sun's hidden field rises into view and leaves visible marks. An active region is not a separate object placed upon the Sun. It is a portion of the Sun's outer layers where magnetic forces become locally intense, organized, and often visibly complex. In these areas, the smooth appearance of the solar disk gives way to structure. Dark sunspots appear. Bright surrounding patches form. Arched magnetic patterns rise above the surface. The solar face, which from Earth often looks even and calm, becomes a map of built tension and uneven motion. A sunspot is the most familiar sign of an active region. It appears dark against the brighter solar surface, though the darkness is relative rather than absolute. A sunspot still shines intensely in human terms. It only looks dark because it is cooler than the surrounding photosphere, the visible layer of the Sun from which most sunlight escapes. In a sunspot, strong magnetic fields interfere with the upward transport of heat from below. The gas there remains somewhat cooler than nearby regions, and so it radiates less visible light. This makes the spot stand out. At the centre lies the darkest part, called the umbra. where the magnetic field is strongest and most vertical. Around it lies a lighter ring called the penumbra, where the field fans outward and the pattern becomes more filamented. Together they create one of the clearest visible signatures of magnetism on the Sun. An active region often contains more than one sunspot. It may appear as a pair, a cluster, or an extended grouping spread across a wider area of the solar surface. These spots are not placed at random. They usually emerge as parts of a larger magnetic structure in which opposite magnetic polarities appear in related positions. One side of the region carries one magnetic sign, and the other side carries the opposite. This pattern reflects the deeper structure of the Sun's magnetic field as it rises from below the surface in loops. Where a loop pierces the visible solar layer and emerges outward, one magnetic polarity appears. Where it bends back and re-enters, the opposite polarity appears. What the observer sees on the surface is therefore only part of a larger magnetic shape. This gives active regions a layered meaning. They are visible features on the Sun, but they are also surface expressions of deeper forces. Beneath the photosphere, hot ionized gas moves constantly. The Sun is made of plasma, which is gas whose particles carry electric charge. Because of this, the motions of the gas and the behavior of the magnetic field remain closely linked. Flowing plasma drags, stretches, and twists magnetic lines of force. When magnetic bundles become concentrated enough, they can rise upward through the outer layers and reach the visible surface. There they create the grouped structure recognized as an active region. The region is not fixed in the way a landform is fixed on a rocky planet. It grows, changes shape, fragments, and decays over days or weeks as the Sun's surface continues to move beneath and around it. The visible surface itself is never still. It churns with convection, the slow overturning of hot gas rising and cooler gas sinking. On smaller scales, this appears as granulation, a mottled pattern of bright cells and darker borders. On larger scales, the Sun also rotates unevenly. Its equatorial regions turn faster than regions nearer the poles. This differential rotation steadily shears magnetic structures over time. In and around active regions, these motions matter greatly. They can separate paired spots, stretch the space between magnetic poles, compress magnetic boundaries, and change the angle at which neighboring magnetic systems lie against one another. The result is not simply the appearance of spots, but the growth of magnetic complexity. Some active regions remain fairly simple. They contain a small number of spots and a magnetic arrangement that is orderly and widely separated. Others become crowded and intricate. Dark cores multiply. Penumbral zones overlap. Opposite magnetic polarities press close together in irregular patterns. These more complex regions are especially important because they reveal how much magnetic stress can accumulate in a limited area, even without discussing later outward events. The structure itself already tells the story. A simple region suggests a more orderly field. A tangled region suggests that the field has been twisted, folded, or forced into tighter configurations by motion below and across the surface. Complexity becomes a sign of stored magnetic strain. Active regions also follow the larger rhythm described in the wider setting of the cycle. Early in a solar cycle, new sunspot groups tend to appear at higher solar latitudes. As the cycle progresses, the average latitude of new regions gradually shifts closer to the solar equator. Over years, this drift creates a broad pattern in the Sun's visible activity. The surface does not fill evenly from pole to equator. It organizes its disturbances in bands that migrate with time. This pattern connects the life of one active region to the deeper magnetic behavior of the star as a whole. a single region can be studied as a local disturbance, yet its position and timing also mark its place in the larger cycle. Brightness around active regions adds another layer of contrast. Near sunspots, one often finds brighter areas called faculae. These are regions where concentrated magnetic fields alter the structure of the visible solar atmosphere and make certain parts appear brighter than average, especially toward the limb of the sun. So the same magnetism that creates dark spots can also produce bright surroundings. The sun's face in an active region therefore becomes a place of contrast rather than uniformity, with darkness, brightness, and magnetic shape all intertwined. It is not simply a damaged patch on an otherwise smooth star. It is a zone where the sun's magnetism becomes locally visible through several different signs at once. Nothing in an active region is entirely static. Spots can grow larger, merge, fragment, or fade. New magnetic flux can emerge into an existing region and reshape it. Older regions can decay as their magnetic concentration disperses across the surface. Over time, the sharp structure softens. Strong fields weaken. The dark contrast lessens. The region dissolves back into the wider photospheric pattern. Yet while it lasts, it marks one of the clearest places where the invisible magnetic life of the sun becomes visible to observation. So this next inward layer of the subject rests on the sun's face itself. The broad cycle narrows into concentrated disturbance. Active regions gather the long solar rhythm into local form, and sunspots make that form visible. Here the sun no longer appears as a steady disk of light alone. It becomes a changing surface shaped by magnetism, motion, contrast, and stored tension. Above the magnetically crowded regions of the sun, the outer atmosphere holds a different kind of tension. This outer atmosphere is called the corona. It is much thinner than the visible surface below, yet it extends far outward and is shaped strongly by magnetism. In active parts of the sun, the corona does not sit as a smooth shell. It arches, loops, brightens, and shifts under the influence of magnetic fields rooted in the layers beneath it. Those fields can hold hot plasma in place for long periods, guiding it along invisible paths and building larger structures above the disturbed surface. What appears below as sunspots and bright faculae appears above as a more spacious architecture of loops and magnetic arcs. In that region, the sun stores strain in a form that is not immediately visible to ordinary sight, but is increasingly clear to instruments that observe the sun in different wavelengths of light. The corona becomes the region where built magnetic stress can stop behaving as a stable structure and begin behaving as an eruption. A solar flare and a coronal mass ejection often arise from this same disturbed magnetic setting, but they are not the same event. A flare is a rapid release of energy in the solar atmosphere. It produces intense radiation across the electromagnetic spectrum, including X-rays and ultraviolet light, and it can also accelerate particles to high energies. A coronal mass ejection, often called a CME, is something more material. It is a large expulsion of coronal plasma and magnetic field from the sun into space. The two often occur together because both are signs that magnetic structures in the corona are rearranging and releasing stored energy. Even so, they should not be treated as identical. A flare is primarily a burst of energy and radiation. A CME is an outward-moving mass of plasma threaded by magnetic field. In many space weather events, the CME matters most for the later geomagnetic response at Earth, because it carries the magnetic structure and solar material that can eventually interact with Earth's magnetic environment. The central physical process behind many eruptions is magnetic reconnection. Reconnection is the breaking and joining of magnetic field lines in a new arrangement, allowing magnetic energy stored in twisted or stressed fields to be converted into heat, motion, and particle acceleration. On the Sun, this process takes place in plasma, where the magnetic field and the charged gas remain tightly linked. When magnetic structures become sufficiently distorted, compressed, or unstable, the old arrangement can no longer persist. The field then reorganizes. In that reorganization, energy that had been stored quietly in magnetic form is released quickly. Some of that release appears as the intense brightening and radiation of a flare. Some can help drive the lifting and ejection of a larger coronal structure outward from the Sun. The important point is that the eruption does not arise from combustion or impact. It is a magnetic event, with plasma responding to the changing field that contains it. In many CME launches, the coronal structure that escapes has the form of a magnetic rope, often called a flux rope. This is not a rope in the solid earthly sense, but a bundle of magnetic field lines wound around one another and filled with plasma. Before eruption, such a structure can remain suspended above the solar surface, held in place by the surrounding magnetic field. It may be associated with a filament or prominence, a cooler and denser structure lying within the corona and supported against gravity by magnetism. If the supporting field weakens, or if magnetic stress grows beyond what the local structure can contain, the suspended system can begin to rise. At first the motion may be slow. Then, if the surrounding magnetic restraint gives way or reconnection continues feeding the escape, the rise can accelerate sharply. At that point, the CME is no longer only a stressed coronal feature, it becomes an outward moving eruption. The launch itself is not a small event. NOAA describes CMEs as large expulsions of plasma and magnetic field from the Sun's corona that can eject billions of tons of material, and NASA describes them as immense clouds of solar material that can expand to millions of miles across as they move outward. Their speed varies greatly. Some leave the Sun more slowly, while others are driven outward at extraordinary speed. That range matters because not every eruption carries the same amount of energy, mass, or magnetic organization. Some remain modest. Some become the large, well-structured expulsions that dominate major space weather episodes. From the Sun's point of view, however, all of them begin in the same basic way. Magnetic stress that had been confined above the surface stops remaining confined and begins to open into outward motion. The visible evidence of launch often requires specialized instruments because the corona is faint compared with a bright solar disk. One of the most important tools is the coronagraph, which blocks the direct light of the Sun so that the surrounding outer atmosphere can be seen more clearly. In such observations, a CME may appear as a bright expanding front or halo of material moving away from the hidden solar disk. These images allow scientists to estimate the timing, direction, and speed of the eruption. They also help separate the Sun's quieter outer flow from the more organized disturbance of a true coronal ejection. Without such observations, much of the launch would remain concealed, because the glare of the Sun overwhelms the faint structures of the corona. The eruption is large in physical scale, yet observationally it still needs careful masking of solar brightness to become fully visible. Not every flare produces a CME, and not every CME is associated with the same visible flare strength. Observations show that flares and CMEs occur together very frequently, but the exact relationship is not one of perfect one-to-one equivalence. They are closely related signs of coronal reconfiguration, yet the Sun does not express every eruption in exactly the same pattern. Some flares remain more confined, releasing energy without launching a large mass ejection. Some CMEs are associated with filament eruptions and broader coronal restructuring that can be more significant than the flare's brightness alone would suggest. This matters because the dramatic flash of a flare is only part of the story. For the larger physical event, the essential issue is whether magnetic and plasma structure truly breaks free from the corona and enters open outward motion. So this region of the subject narrows from the crowded solar face into the corona above it, where stored magnetic strain becomes release. The active region below provides the setting, but the launch belongs to the Sun's outer atmosphere. There, loops, ropes, and suspended plasma cease to hold their former shape. Magnetic fields reconnect. Radiation surges in a flare. A cloud of plasma and embedded field can then rise and separate from the Sun as a coronal mass ejection. In this moment, the Sun changes from a star storing disturbance to a star sending disturbance outward. The eruption is the point at which hidden magnetic tension becomes motion. Once the coronal mass ejection leaves the Sun, it enters a region that is neither empty nor still. The space between the Sun and Earth is often imagined as a silent void, but in physical terms it is filled by the solar wind. The continuous outward flow of charged particles and magnetic field that streams away from the Sun in all directions, filling the heliosphere around the planets. This wider flow is thin, but it is real, and it forms the background medium through which any ejected cloud from the Sun must travel. A coronal mass ejection does not move through a perfect vacuum as an isolated object. It pushes into an already moving environment, and that environment affects its speed, shape, and direction as it travels outward. The storm cloud that has just broken free from the corona now becomes an interplanetary traveler, carrying solar plasma and magnetic field while being reshaped from the first moment of departure by the larger solar wind around it. This passage across interplanetary space can be fast on human terms and slow on solar terms at the same time. The distance from the Sun to Earth is about 150 million kilometers, and even a powerful eruption requires time to cross it. NOAA states that the fastest Earth-directed coronal mass ejections can arrive in as little as about 15 to 18 hours, while slower ones can take several days. NASA and NOAA also commonly describe Earth-directed coronal mass ejections as reaching Earth in roughly 1 to 3 days. These ranges show that there is no single travel time. The transit depends on the initial speed of the eruption, the magnetic and plasma conditions through which it moves, and the way the ejected cloud expands as it goes. A storm launched with great force can race outward. A slower one can drift through the solar wind more gradually. In both cases, the journey is not a clean, straight-line motion of a rigid body. It is a broad, moving structure evolving through a flowing medium. Expansion is one of the key features of that evolution. As the ejected cloud travels farther from the Sun, it tends to grow in size. NOAA notes that larger events can expand to nearly a quarter of the distance between the Sun and Earth by the time they arrive near Earth. This means that the storm is not best understood as a compact ball launched outward unchanged. It spreads, broadens, and occupies an increasingly large volume of interplanetary space. The plasma within it thins as the structure enlarges, yet the magnetic organization can remain important over vast distances. What leaves the Sun as a coronal eruption becomes, during transit, a much larger interplanetary disturbance. If the ejection moves faster than the surrounding solar wind, another structure can form ahead of it. NASA describes fast coronal mass ejections as building up dense fronts that form shocks when they move faster than the local solar wind. A shock in this context is a sharp transition, where plasma properties such as density, speed, temperature, and magnetic field change abruptly. It is not a sound wave in the ordinary earthly sense. Instead, it is a moving compression in the charged gas and magnetic field ahead of the ejection. This shock can sweep particles up, accelerate them, and mark the leading edge of a more forceful disturbance moving through interplanetary space. Behind that leading shock, the main body of the ejected cloud continues outward, still carrying its own magnetic pattern. Observations from ESA's solar orbiter also show that fast-forward shocks can be driven through interplanetary space by coronal mass ejections. The ambient solar wind does not simply receive this traveller without influence. It can slow a fast ejection by drag-like interaction, and it can sometimes allow a slower one to be carried along more efficiently by the surrounding flow. The Sun is also producing more than one structure at a time. High-speed streams from coronal holes, slower, denser solar wind, and earlier eruptions can all shape the path of a later event. Observations indicate that some interplanetary storms interact with material already present in space, including remnants of previous ejections. This means that the route from Sun to Earth is not always a single storm moving through a quiet background. It can be a moving disturbance entering a dynamic and structured heliosphere, the vast solar region filled by the Sun's outward influence. Direction matters as much as speed. Many ejections leave the Sun in directions that do not place Earth in their main path. Some spread partly across Earth's orbital region, but remain weak at Earth because their strongest core misses the planet. Some appear as halo events in coronagraph images, expanding around the blocked solar disk in a way that suggests motion broadly toward or away from the observing spacecraft. Even then, the exact orientation and internal magnetic structure of the storm remain important and are not always fully known from the first images alone. A coronal mass ejection seen leaving the Sun is therefore not yet a fully solved event. It is a moving magnetic cloud whose later influence depends on the geometry of its travel as much as on the fact of its launch. For this reason, scientists watch the transit continuously with models and spacecraft placed at useful vantage points. NOAA uses large-scale heliospheric models to provide 1 to 4 day warning of solar wind structures and Earth-directed coronal mass ejections. These models combine solar observations with the physics of the ambient flow to estimate arrival times and likely strength. Spacecraft upstream of Earth also sample the solar wind before it reaches the planet, providing a nearer look at the approaching disturbance during the final stage of transit. Yet even with these tools, uncertainty remains. A storm can speed up, slow down, expand unevenly, or interact with other solar wind structures in ways that complicate simple prediction. What can be known with confidence is the broad fact of passage after launch. The storm spends hours to days crossing a region that is active, magnetized, and far from empty. So this region of the story belongs to the long corridor between Sun and Earth. The eruption has already occurred, but the sky above Earth has not yet changed. The storm is in transit, carrying solar material and magnetic structure across interplanetary space, expanding as it goes, sometimes driving a shock before it, and moving through the background river of the solar wind. In this interval, the event is no longer only a solar eruption, yet it is not yet a terrestrial disturbance. It is a travelling structure in the heliosphere, shaped by distance, motion, interaction, and time. As the storm approaches Earth, one feature becomes more important than speed alone. The moving cloud carries its own magnetic field, and the direction of that field strongly affects how powerful the encounter can become. A coronal mass ejection is not only a mass of solar plasma crossing interplanetary space, it is also a structure threaded with magnetic lines of force, shaped by the magnetic conditions in which it formed and altered further during its journey outward. By the time it nears Earth, the storm may still hold a recognizable internal organization, sometimes with a smoother magnetic core and sometimes with a more disturbed outer region. In either case, the field direction inside the arriving solar material matters greatly. A fast storm can still produce a limited response if its magnetic orientation is unfavorable for deep interaction. A somewhat slower storm can become far more effective if its field arrives in the right direction. At this outer stage near Earth, the problem is no longer only whether the storm arrives, but how its magnetism is aligned when it does. The magnetic field carried outward from the Sun through the solar wind is often called the interplanetary magnetic field. In simple terms, it is the portion of the Sun's magnetic influence that extends through the space between the planets, embedded in the outward flowing plasma. Under ordinary conditions, this field already varies in strength and direction. During a storm, the arriving structure can intensify it and organize it in ways that become especially significant for Earth. Scientists often pay close attention to the north and south component of this field relative to Earth's own magnetic orientation. This part of the storm's field is important because Earth's magnetic field near the sunward side points generally northward at the boundary region facing the Sun. If the approaching interplanetary field also points northward, the two systems tend to lie in a more parallel arrangement. If the approaching field points southward, the two systems oppose each other in direction, and the encounter can become much more effective in transferring energy. This is why the southward component is so closely watched. Southward here does not mean downward toward Earth's surface in the ordinary geographic sense. It means southward in magnetic orientation relative to the northward direction of Earth's outer field on the day side. The distinction matters because the sky does not reveal this directly. The storm may look impressive in coronagraph images while still leaving uncertainty about the internal direction of its field. Even when the cloud is clearly Earth-directed, its magnetic structure can arrive in a form that is weakly southward, strongly southward, mixed, or shifting over time. That variation changes the outcome. A sustained southward field usually allows a much stronger coupling between the storm and Earth's magnetic environment. A northward field tends to reduce that efficiency. The same broad storm can therefore produce very different terrestrial effects depending on a property that remains invisible to ordinary sight. The approaching cloud often does not carry one single, fixed direction throughout its entire body. Its outer disturbed region may contain compressed and fluctuating magnetic fields. Farther inward, the main magnetic structure may rotate gradually through different orientations as Earth passes through it. This means that the key southward interval may begin suddenly, last for hours, weaken, return, or never become strong at all. Space weather, therefore, depends not only on whether Earth is struck by the storm, but on which part of the storm arrives first and how the internal field turns during passage. A storm with a brief southward interval may produce a more limited response than one with a long, steady southward interval, even if both are large eruptions from the Sun. Duration matters along with strength. A field that stays southward for a sustained period gives Earth's outer magnetic environment more time to respond strongly. There is also a difference between compression and orientation. A storm can compress the near-Earth space environment simply by arriving with high speed and pressure. Compression alone can produce measurable effects. Yet the more dramatic geomagnetic response depends heavily on direction as well as force. Pressure can push. Orientation determines how deeply the storm's magnetism can interact. That is why forecasts often remain cautious until direct measurements of the arriving solar wind and magnetic field become available from spacecraft positioned upstream of Earth. Before those measurements, scientists may know that a large eruption is coming and may estimate its likely arrival time, but they may still lack certainty about the most important inner property of all, The magnetic field inside the storm remains one of the last critical unknowns. A strong southward component can turn concern into a major event. A weak or mostly northward field can reduce the disturbance considerably. The reason direction matters so much lies in the geometry of magnetic systems. Fields aligned in similar directions tend to remain more separate. Fields brought together in opposing directions more readily change connection and release stored tension into motion. At this stage, it is enough to say that Earth's magnetic shield responds very differently depending on whether the arriving field matches or opposes its orientation. The southward case is the one that opens the way for stronger transfer. The northward case is the one that resists it. In that sense, the interplanetary storm carries a hidden decision within itself. Long before the aurora changes over the poles, the field direction in the approaching cloud has already set broad limits on what kind of encounter Earth is about to experience. This makes the near-Earth arrival of a solar storm a subtle moment. The storm is no longer only a traveller from the sun. It is now a structured magnetic presence close enough for its internal orientation to matter immediately. It may carry turbulence, compression, plasma, and speed. But the most important question at this outer threshold is whether its magnetic field turns southward and how long it remains that way. That one geometric fact can determine whether the encounter stays moderate or becomes much stronger. The sky on Earth still shows nothing yet to ordinary daylight sight. The crucial change at this region of the story is still invisible. It exists in the direction of a field embedded in a moving cloud of solar plasma just outside Earth, where alignment quietly begins to decide the force of what follows. The first physical boundary Earth presents to an arriving solar storm is not the atmosphere and not the surface of the planet. It is a shock standing far out in space, upstream from the main magnetic shield. This is the bow shock. It forms because carries enough organized motion that it cannot simply drift gently around Earth's magnetic obstacle. Earth's magnetic field creates a cavity in the solar wind, a protected region often called the magnetosphere, and the incoming flow must adjust to that obstacle before it can pass around it. The adjustment does not happen smoothly at great speed. A shock forms instead, rather like the compressed boundary that appears ahead of a ship moving through water or ahead of an object moving faster than sound through air. Though here the medium is not ordinary gas but hot ionized plasma threaded by magnetic field. At this outer threshold, the storm first ceases to be a freely streaming solar disturbance and becomes a disturbance meeting resistance. The bow shock stands sunward of Earth, facing the direction from which the solar wind arrives. It is not a fixed shell with a rigid shape. It breathes inward and outward depending on the pressure and speed of the incoming flow. During stronger solar wind conditions, and especially during the arrival of a storm, the whole system can be pushed closer to Earth. During quieter conditions, it can relax farther outward. Even so, the general geometry remains recognizable. On the day side, where the solar wind first meets Earth's magnetic obstacle, the bow shock lies ahead of the magnetosphere as the first major transition in the encounter. It marks the place where a fast magnetized flow is forced to slow, compress, and change character before continuing inward toward the next boundary. The incoming solar wind is described as supersonic. Though this needs care in a plasma environment, it does not mean sound in the ordinary human sense moving through air. It means the solar wind is moving faster than Keywave speeds, by which information and pressure changes can travel through the magnetized plasma. Because of this, the upstream flow cannot gradually sense the obstacle and turn aside long in advance. The information that Earth's magnetic field presents a barrier cannot move upstream quickly enough through the oncoming flow, so the adjustment becomes abrupt. The bow shock is the place where that abrupt change happens. Across it, the solar wind slows from supersonic to subsonic speed, and part of its organized bulk motion is converted into heat, turbulence, and compressed magnetic structure. What was a fast stream becomes a hotter, denser, more disturbed region. This slowing is not merely a drop in speed. The plasma changes state, density rises, temperature rises, magnetic field strength can increase. The flow also becomes more irregular. Fluctuations, waves, and fine structure appear in and around the shock. The incoming storm therefore does not simply strike a clean invisible wall. It passes through a transitional zone in which motion, heat, and magnetic pressure are redistributed. The bow shock is both a boundary and a process. It is a surface in the broad geometric sense, but it is also a region of conversion where streaming energy is turned into other forms. That is why it matters so much to the overall encounter. Before the solar wind can be redirected around Earth's magnetic field, it must first be prepared by this shock. Behind the bow shock lies the magnetosheath. This is the region between the bow shock and the magnetopause, the outer boundary of the magnetosphere itself. In the magnetosheath, the solar wind no longer moves with the cleaner, faster character it had farther upstream. It has been compressed, heated, and slowed, and now it flows around the magnetic obstacle presented by Earth. The magnetosheath is therefore not empty space between two sharper lines. It is a broad sheath of disturbed plasma, filled with altered solar wind that has already passed through the first great transition. Here the storm spreads and wraps around the planet's magnetic cavity. Flow lines curve, pressure redistributes, the plasma remains solar in origin, but it no longer resembles the more uniform wind that approached from interplanetary space. The storm's arrival can make this entire dayside region more compact and more active. Greater solar wind pressure pushes the bow shock inward and strengthens compression. The magnetosheath can become denser and more forceful as the arriving disturbance piles up against the magnetosphere. Yet the important fact at this stage is still one of boundary physics rather than deeper transfer. The storm has reached Earth's outer obstacle, but it has not simply crossed unchanged into the protected magnetic domain. It has first been shocked, heated, and deflected. The existence of this boundary reminds astronomy that Earth's interaction with the Sun is not a bare impact on the atmosphere. A series of space boundaries intervenes, and the bow shock is the first of them during the storm encounter. The bow shock also has internal variety. It does not behave identically at every location or under every magnetic orientation of the incoming solar wind. The angle between the upstream magnetic field and the shock surface affects how particles move and how sharply the transition forms. Some parts of the shock can be more turbulent. Some can reflect particles back upstream, creating a disturbed region ahead of the shock itself. Waves can travel through the surrounding plasma, and the shock can shift or ripple rather than remain perfectly smooth. The overall picture stays clear despite this complexity. A standing shock forms because the solar wind meets an obstacle too suddenly and too forcefully to adjust in a gradual way. But within that general picture, the boundary remains alive with small-scale structure and changing behavior. This makes the dayside outer environment of Earth more dynamic than the word boundary might suggest. A boundary in ordinary life often implies stillness, like a coastline or a wall. The bow shock is not like that. It is a constantly renewed transition sustained by the continuous flow of solar wind. Every moment, new plasma arrives from the Sun and passes through the same broad process of compression and deceleration. During a solar storm, the pace and intensity of that renewal increase. The incoming plasma carries stronger pressure, stronger magnetic organization, or both, and the shock responds accordingly. It does not wait. It exists only because the flow continues. So this region of the story belongs to Earth's outermost response to the oncoming storm. The freely travelling disturbance from interplanetary space meets the first standing structure of the near-Earth environment. At the bow shock, the storm slows. In the magnetosheath, it becomes a compressed and heated flow that bends around the magnetic obstacle of the planet. Earth still has not revealed its deeper magnetic response here. The process remains at the threshold. Yet already the storm has changed character. It is no longer only a cloud from the sun crossing open space. It is now solar wind that has encountered resistance, passed through shock, and entered the disturbed sheath surrounding Earth's magnetic domain. Inside the disturbed sheath of slowed solar wind, the next decisive boundary is the magnetopause. This is the outer edge of Earth's main magnetic cavity, the place where the pressure of the incoming solar wind is balanced against the pressure of Earth's magnetic field. It is not a rigid surface like the wall of a vessel. It is a moving boundary shaped continuously by the flow outside and the magnetic strength inside. On the day side, facing the sun, it marks the place where Earth's field stands directly against the solar wind and tries to preserve a protected domain around the planet. In quiet conditions, this boundary holds its general form without great disturbance. During a solar storm, it is pressed inward, stressed more strongly, and brought into more intense contact with the magnetic field carried by the arriving solar material. At this boundary, the geometry of the storm's field begins to matter in a profound way, because the magnetopause is not only a line of separation, it is a place where magnetic systems can change connection. Earth's magnetic field on the day side points generally northward across much of this outer region. When the approaching interplanetary field also points northward, the two fields tend to lie alongside one another in a more parallel arrangement. The magnetopause still exists under pressure, and the solar wind still flows past, but deep coupling is less efficient. When the approaching field points southward, the situation changes. Oppositely directed magnetic fields are brought together at the boundary. Under those conditions, the field geometry favours a process called magnetic reconnection. Reconnection is the breaking and joining of magnetic field lines into a new pattern. It is not a cutting of physical wires. It is a topological change in a magnetized plasma, where the magnetic structure rearranges and in doing so allows stored magnetic energy to be converted into motion, heat, and particle acceleration. At the dayside magnetopause, reconnection is the process by which the storm begins to open a path across what would otherwise be a more resistant magnetic shield. Before reconnection, Earth's dayside magnetic field lines can be imagined as closed loops. They emerge from one polar region, arc outward through space, and return to the other polar region, remaining attached to Earth at both ends. The interplanetary field carried by the solar wind is different. It belongs to the outward magnetic structure of the Sun and is threaded through the passing plasma flow. When oppositely directed portions of these two systems meet at the magnetopause, they can reconnect and form a new geometry. A formerly closed Earth field line can become joined to the interplanetary field. The result is an open field line, attached to Earth at one end and to the solar wind at the other. This is one of the most important quiet changes in space weather. A boundary that had separated two domains becomes, in selected places, a region where the domains become linked. This opening does not happen equally everywhere at all times. It depends on local magnetic orientation, plasma conditions, and the rate at which the solar wind is driving the system. During a storm with a sustained southward field, reconnection on the day side can become much more extensive and efficient. The boundary is then no longer merely compressed from the outside, it is also being magnetically eroded. Closed dayside flux is converted into open flux. Earth's dayside shield still exists, but part of its outer magnetic structure is being peeled back into new connections with the solar wind. This is why a southward field is so important. It does not merely press on the magnetosphere more strongly, it changes the way the boundary behaves. The magnetopause therefore becomes an active gate rather than a passive edge. Solar wind energy does not enter only by brute force. It enters through a geometric and physical process that reorganizes magnetic structure. Plasma near the reconnection region can be accelerated away from the site. Electric fields arise. Magnetic tension in the newly connected field lines pulls them into motion. The system begins to behave less like a fixed obstacle in a stream and more like a coupled magnetic engine, driven by the interaction of two field systems with opposing directions. At the center of this is the reconnection site itself, a narrow region where the field changes connection and where ideal magnetic separation between the two domains breaks down. Observations show that the dayside magnetopause is not smooth and unchanging while this happens. Reconnection can occur in bursts or in more continuous intervals. It can be patchy along the boundary. Spacecraft crossing the dayside magnetopause have detected signatures of this process in flowing plasma jets, magnetic rotations, and moving structures often called flux transfer events. These are transient bundles of newly connected magnetic flux that travel along the magnetopause and reveal that the boundary is locally and temporarily opening. Their existence shows that reconnection is not just an abstract idea used to describe the magnetosphere in broad terms. It leaves measurable marks in the motion and magnetic structure of the boundary itself. The gate opens not as a single theatrical moment, but as a sequence of real plasma events occurring in the outer magnetic environment of Earth. There is also a balance in this process. Earth's field does not disappear when reconnection occurs. The magnetosphere remains a distinct system with its own pressure, internal currents, and broad geometry. What changes is the extent to which the solar wind can couple to it. Reconnection increases that coupling. It gives the external flow a way to transfer energy and momentum into the terrestrial magnetic domain. The stronger and more sustained the southward driving field, the more effective this transfer can become. A storm therefore becomes powerful not only because it arrives fast or compressed, but because it finds a favourable configuration at the boundary and keeps that configuration long enough for significant magnetic opening to continue. At the dayside magnetopause, Earth's outer magnetic environment also reveals an important truth about shielding. A shield is often imagined as something fully closed and impenetrable. Earth's magnetic field is more subtle than that. It protects the planet by standing off the solar wind and shaping a large cavity in space. Yet its boundary is not perfectly sealed under all conditions. Under the right magnetic orientation, it can connect. Protection remains, but it becomes dynamic rather than absolute. The shield works through structure and motion, not through complete isolation. Reconnection is part of that working. It is a controlled failure of separation in one sense, and a natural operating mode of a magnetized planet in another. So this region of the story belongs to the dayside gate of Earth's magnetic shield. The storm has crossed interplanetary space, past the bow shock, and entered the compressed sheath outside the magnetosphere. At the magnetopause, its southward magnetic field meets Earth's northward field in the geometry most favourable for change. Reconnection opens part of the boundary. Closed terrestrial field becomes open. Energy begins to pass inward more efficiently. Nothing is yet visible in the sky from this process alone. The essential event here remains magnetic and silent. A boundary facing the sun begins to yield, not by collapse, but by connection. On the night side of Earth, opposite the sun, the magnetosphere does not keep the rounded dayside form that faces the solar wind. It is drawn out into a long magnetic extension called the magnetotail. A tail, in this sense, is the elongated nightside part of Earth's magnetic domain, stretched away from the sun by the continuous pressure and flow of the solar wind. The dayside magnetosphere is compressed. The nightside magnetosphere is pulled long. This broad shape exists even in quieter conditions, but during a strong solar storm the stretching becomes more pronounced and more important. Energy that enters through the dayside boundary does not remain only near the point of entry. The geometry of Earth's magnetic field carries that effect across the polar regions and into the night side, where the field is extended into a long two-lobed structure with a central sheet of plasma and current between them. In this region, the magnetosphere does not simply endure the storm, it stores part of the storm's influence in magnetic form. The magnetotail is not a narrow filament trailing behind the planet like smoke behind a moving object. It is a vast region of near-Earth space shaped by Earth's field and by the solar wind flowing around it. Its broad form can be understood through a simple picture. Field lines on the night side are pulled away from the planet so that the tail becomes divided into two large magnetic lobes, one above and one below the central plane. In the northern lobe, the magnetic field points generally toward Earth. In the southern lobe, it points generally away from Earth. Between these two lobes lies a thinner central region called the plasma sheet, where the magnetic field is weaker, the particle population is denser, and electric currents flow across the tail from dawn toward dusk. This arrangement gives the nightside magnetosphere a layered structure. The lobes hold strong stretched field. The central sheet carries hotter plasma and current. Together they form the main architecture of the magnetotail. When reconnection on the dayside magnetopores opens more of Earth's magnetic flux, those newly opened field lines do not remain on the dayside. The solar wind drags them anti-sunward across the polar caps and into the magnetotail. There they become part of the tail lobes. This process increases the amount of open magnetic flux stored in the tail and strengthens the stretched configuration of the nightside field. In simple terms, the tail becomes more loaded. More magnetic field is drawn into it. More tension is carried by the long nightside structure. The solar storm therefore affects the magnetotail not by direct pressure alone, but by changing the magnetic inventory of the system. Field that once belonged to a more closed dayside arrangement is transferred into the nightside tail, where it contributes to a larger reservoir of stored magnetic energy. Magnetic energy is not a metaphor here. A magnetic field under tension stores real energy in its configuration. A stretched field contains more energy than a more relaxed one, just as a pulled elastic band holds energy because of its deformation. The comparison is limited, since magnetic fields in space are not material chords, but it helps show why stretching matters. In the magnetotail, the storm-driven flow of open flux increases the tail's magnetic pressure and tension. The lobes become more strongly magnetized. The field lines are drawn into a longer and more tail-like form. The central plasma sheet can thin as the lobe field strengthens and presses inward from above and below. The whole nightside system takes on a more loaded structure. Nothing bright or visible happens in the night sky because of this loading alone. The change belongs first to the invisible organization of Earth's magnetic domain. The lobe regions themselves are comparatively sparse in plasma. They are dominated by magnetic field rather than by dense particle populations. That is one reason they are effective storage regions. The field there can become strong and organized over large distances, while the central plasma sheet between the lobes remains the main repository of hotter particles and electric current. The current sheet, or crosstail current sheet, is especially important to the structure of the magnetotail. It separates the opposite magnetic directions of the northern and southern lobes and helps maintain the tail's overall balance. As loading increases, this current system can intensify, and the central sheet can become thinner and more stretched. The nightside magnetosphere then reflects the storm not as a simple bulk shift, but as a reorganization of magnetic tension, plasma distribution, and current flow. Distance matters in this region, but not in the same way it mattered between the Sun and Earth. The magnetotail extends very far downstream from the planet, and spacecraft sample only parts of it at different times and distances. Even so, the basic structure is clear from decades of observations. Nearer Earth, the tail remains strongly connected to the rest of the magnetosphere and reflects the immediate response to solar wind driving. Farther down the tail, the stretched geometry continues into a long nightside extension, whose exact limits depend on how one defines Earth's magnetic influence in the solar wind flow. What matters most here is not the farthest possible boundary, but the fact that the nightside magnetic system is spacious enough to store large amounts of energy as the storm continues to drive it. Earth's response is not confined to a thin shell around the dayside. It reaches deep into the nightside volume of the magnetosphere. The loading of the magnetotail is often described as a growth phase in magnetospheric activity, though the important point in this region is simply the growth of stored magnetic stress. As more open flux is added to the tail lobes, the polar cap can expand and the tail becomes more stretched. The configuration remains dynamic, because solar wind driving continues while plasma circulates within the magnetosphere. Yet the overall tendency under sustained southward driving is toward greater tail loading. Energy that comes from the solar wind is not immediately spent. Part of it is held in the magnetic form of the nightside system. This is one of the key quiet truths of auroral storms. Before light changes in the upper atmosphere, the magnetosphere first changes in shape and internal tension. The magnetotail also shows that Earth's magnetic field is not a simple dipole in practice during disturbed times. Near the planet, the field retains the broad character of a dipole, with northern and southern polar regions and field lines looping between them. Farther out on the night side, solar wind forcing transforms that simpler geometry into something longer, flatter, and more stratified. The tail lobes, plasma sheet, and cross-tail current are not incidental details. They are the nightside form that Earth's magnetosphere takes when embedded in a flowing solar wind. During a storm, that form becomes more extreme. The field stretches farther from the rounded image often associated with the simple bar magnet. It becomes a long repository of directed magnetic stress in near-Earth space. So this region of the story belongs to the nightside storage of energy. The storm has already reached Earth, crossed the outer boundaries, and opened the dayside magnetic shield in places. Now the effect is carried over the polar regions and into the long dark extension behind the planet. There the magnetotail grows more loaded, its lobes more tense, its central sheet thinner and more active in current, and its overall structure more stretched by the continued transfer of solar wind energy into Earth's magnetic system. The sky remains outwardly unchanged in this region. The essential event is still hidden in space behind the planet, where the magnetosphere stores the storm in magnetic form. A magnetotail loaded with magnetic stress does not remain in that stretched condition indefinitely. As the nightside field becomes more extended and the central plasma sheet grows thinner, the configuration becomes increasingly favorable for a sudden internal reorganization. This is the stage at which stored magnetic energy begins to shift from quiet tension into rapid release. The process is again magnetic reconnection, but here it occurs not on the dayside boundary facing the sun, but deeper in the nightside tail where oppositely directed magnetic fields in the northern and southern lobes are brought close together across the thinning central current sheet. The tail, which has been storing solar wind energy in stretched form, begins to change its shape. The long-drawn structure starts to give back part of what it has been holding. In the magnetotail, the northern and southern lobe fields point in opposite directions. Between them lies the plasma sheet and the current sheet that separates the two lobes. As loading increases, that central sheet can become thinner and more intense, creating conditions in which reconnection becomes possible within the tail itself. When this happens, field lines that had been stretched far from Earth change connection in a new pattern. Some reconnect in a way that produces closed field lines connected to Earth at both ends and moving earthward. Others reconnect into field lines that are no longer tied to Earth on both ends and are carried farther down the tail, away from the planet. This is one of the most important dividing moments in the storm response. The tail stops behaving mainly as a storage reservoir and begins behaving as a release system. The release does not empty the entire magnetotail at once. It begins in a more localized region, often called the near-Earth neutral line, where the reconnection process becomes active within the nightside plasma sheet. From that region, consequences spread in two broad directions. Down the tail, newly reconnected field and plasma can be expelled away from Earth in a moving structure often described as a plasmoid, a magnetic and plasma bundle carried down the nightside extension of the magnetosphere. Toward Earth, reconnected field lines contract because magnetic tension pulls them into a less stretched shape. This contraction drives fast earthward flows of plasma and field. The nightside system is therefore split between release outward and release inward. One part of the tail lets energy go by ejecting structure away from the planet. Another part sends energy and motion back toward the inner magnetosphere. These earthward flows are not gentle. When stretched field lines reconnect, the resulting closed field lines are shorter and less tail-like than the ones from which they formed. Magnetic tension pulls on them strongly, and that pull accelerates plasma earthward through the plasma sheet. Fast flow bursts move inward, carrying magnetic flux and energy toward regions closer to the planet. At the same time, the magnetic field nearer Earth begins to change from its previously stretched state toward a more dipole-like form. This process is often called dipolarization. The term refers to the field becoming more like the familiar rounded dipole shape of Earth's nearer magnetic field and less like the long, flattened shape of the distant tail. Dipolarization is therefore one of the clearest signs that the nightside field is relaxing after a period of loading. This sudden reconfiguration of the tail is what gives a magnetospheric substorm much of its character. A substorm is not the same as the full global magnetic storm driven by prolonged solar wind conditions, though the two often occur together during disturbed times. A substorm is a shorter, more explosive release of energy stored in the magnetotail. It marks the expansion phase of nightside activity after a growth phase of loading. In simple terms, the storm provides the broad forcing and loading of the system, while the substorm is one of the ways the nightside magnetosphere releases the energy it has accumulated. The word substorm does not mean small in the everyday sense. It means a distinct magnetospheric disturbance nested within the larger context of geomagnetic activity. The tail release also changes the pressure balance and current systems of the nightside magnetosphere. As reconnection proceeds and earthward flows intensify, the crosstail current can weaken in the region, affected by depolarization. Magnetic energy that had been stored in the stretched lobe field is converted into plasma motion, heating, and altered current patterns. The night-side magnetic configuration becomes less taut, yet the process is not smooth. It can unfold in bursts, with flow channels, localized fronts, and repeated reconfigurations rather than one continuous quiet relaxation. The plasma sheet can become highly dynamic, and the earthward moving fronts can compress and energize plasma as they travel. What had been a long reservoir of stored tension becomes a region of rapid transport and conversion. There is also a strong spatial pattern to this release. The magnetotail is large, and the reconnection region does not encompass all nightside space equally. Some regions become active while others remain comparatively less affected at a given moment. The earthward moving consequences are also modified by the stronger magnetic field closer to Earth. As inward flows approach the inner magnetosphere, they cannot simply continue unchanged. The stronger dipole-like field nearer the planet slows, diverts, and redistributes them. This produces further breaking, compression, and reorganization of plasma and magnetic structure. The night-side magnetosphere during substorm expansion is therefore not a simple pipe down which energy moves inward. It is a layered system in which release in the midtail region drives changes all the way toward the inner magnetic domain, while other parts of the release structure are simultaneously expelled downtail. The essential calm truth of this region is that a surge in auroral activity begins long before visible light changes in the upper atmosphere. The first sudden turning point occurs invisibly in the tail behind Earth. Magnetic fields that were stretched by solar wind driving begin to reconnect. Energy stored over time is released within minutes. Part of the tail's magnetic tension is transformed into moving plasma, altered currents, and a field that becomes less tail-like and more dipolar again. The magnetosphere does not merely absorb the solar storm, it actively rearranges itself in response, and the substorm is one of its most characteristic expressions of that rearrangement. So this region of the story remains entirely on the night-side magnetic side of the event. The outer boundaries and dayside gate have already allowed energy to enter. The magnetotail has stored that energy in stretched form. Now the tail releases it. Reconnection begins within the night-side plasma sheet. Some structure is expelled farthest down the tail. Some returns earthward in fast flows. The magnetic field nearer Earth begins to recover from its stretched state. The substorm is therefore the moment when the loaded night-side system snaps into more active motion and begins to spend the energy it has been holding. After the night-side tail releases stored magnetic energy, that energy does not remain scattered through the tail itself. Part of it is directed into pathways that lead back toward the planet along Earth's magnetic field. These pathways are not broad channels of ordinary motion through empty space. They are guided routes defined by magnetic geometry. Charged particles in near-Earth space do not move freely in whatever direction they choose. Because they carry electric charge, their motion is strongly shaped by magnetic fields. In simple terms, they tend to spiral around magnetic field lines while also moving along them. This combination creates helical motion, a corkscrew-like path around an invisible line of force. When the magnetotail becomes active and releases energy, large populations of electrons, and to a lesser extent ions, are directed into these field-guided paths. The result is a set of polar particle streams flowing toward the high-latitude regions of Earth's magnetic environment. Earth's magnetic field near the planet has a broad dipole form, with field lines that rise from one polar region, arc through space, and return through the other, on the night side. The more distant field is stretched into the magnetotail, but closer in, the magnetic geometry still provides connected paths between the tail-connected magnetosphere and the polar regions. After reconnection and dipolarization in the tail, plasma and energy are driven earthward. Some of that energy is carried not by bulk flow alone, but by particles redistributed onto field lines that thread into the auroral zones. The auroral zones are the high-latitude magnetic regions encircling each pole, where these particle streams most often enter the upper atmosphere. At this stage, however, the important fact is the guided motion in space itself. The particles are being sorted and directed by magnetic structure long before any visible display appears below. Electrons are especially important in this process because they are light and respond rapidly to electric and magnetic forces. In the disturbed night-side magnetosphere, electric fields arise as the magnetic configuration changes. Some of these electric fields act across the magnetic field, driving large-scale convection of plasma through the magnetosphere. Others can develop along the magnetic field in localized regions, especially during disturbed intervals, and these can accelerate electrons downward toward Earth. A field aligned with the magnetic line is important because motion along the field is the direction in which charged particles can most readily travel. When such parallel electric fields appear, they can increase the directed energy of the electrons moving earthward. This does not happen everywhere in a uniform way. It occurs in structured regions linked to the broader current system of the disturbed magnetosphere. These linked current systems are often called field-aligned currents, or Birkeland currents. A current in this setting means a collective motion of charged particles, not a wire carrying electricity in the ordinary earthly sense. Field-aligned currents flow along magnetic field lines between the magnetosphere and the high-latitude ionosphere. They form part of the large-scale electrical coupling between space and the upper atmosphere. During magnetospheric disturbance, these currents intensify and help organize where energy and particles travel. In some regions, electrons move downward toward Earth. In other regions, particles move upward away from the upper atmosphere. The system is not one simple one-way rain of particles across the entire polar region. It is a structured arrangement of connected upward and downward current channels. For the brightening auroral regions, the downward moving electrons are especially important because they carry energy into the upper reaches of the atmosphere. The magnetic field lines themselves converge as they approach Earth. Far out in space, neighboring field lines can be widely separated. Closer to the planet, they crowd together toward the polar regions. This convergence affects the particle streams in a powerful way. A population of particles spread across a larger magnetic tube farther out can become concentrated into a smaller physical area nearer Earth. The result is a focusing effect. The particles do not necessarily increase in total number simply because of convergence, but they are guided into narrower footprints at high latitude. This helps explain why auroral activity is organized in arcs, bands, and oval-shaped regions rather than spread evenly across all latitudes. The magnetic geometry narrows the paths and directs them toward specific zones. Not every particle moving along a field line reaches the same depth or keeps the same direction. As particles spiral inward along converging field lines, the magnetic field strength increases. This stronger field can reflect some particles back outward if their motion is not sufficiently directed along the field line. This effect is called magnetic mirroring. In simple terms, a particle with too much of its motion wrapped into the spiral around the field and too little motion directed along the field can be turned back before travelling farther inward. Only particles within a certain range of motion relative to the field, often described as the loss cone, continue all the way downward. This means the auroral particle stream is not a random sample of all magnetospheric particles. It is a filtered population, shaped by magnetic geometry, electric acceleration, and the changing field strength encountered on the way toward Earth. During active conditions, the downward electron population can become highly structured in time and space. There can be broad diffuse precipitation, in which larger regions receive more modest streams of particles, and there can also be narrower, more intense beams associated with more sharply organized auroral forms. Some of these differences reflect where in the magnetosphere the particles originate. Some reflect how strongly they are accelerated on the way down. Some reflect the pattern of field-aligned currents and the spatial structure of the disturbed nightside system. The key calm truth of this region is that the magnetosphere does not simply empty itself uniformly toward the poles, it selects, channels, and organizes particle motion into coherent streams. Ions also participate, though often in a different balance and with different energy ranges, because ions are much more massive than electrons. They respond more slowly to some forms of acceleration and do not dominate the visible auroral energy input in the same way electrons often do. Still, ions can travel along the same broad magnetic pathways and contribute to the overall energy and momentum exchange between the magnetosphere and the polar upper atmosphere. In some disturbed intervals, upward ion outflow from the high-latitude atmosphere also becomes important, feeding material from the upper atmosphere into the magnetosphere. This shows that the polar connection is not one-directional in every detail. It is a coupled system, yet for the bright surge that concerns this subject, the downward-directed electron streams remain central. So this region of the story belongs to the invisible descent of charged particles through Earth's polar magnetic architecture. The magnetotail has already released stored energy. That energy is now guided along field lines through organized current systems and narrowing magnetic pathways toward the high-latitude regions around both poles. Electrons are accelerated, selected, and concentrated. Some are mirrored back, some continue downward in structured streams. The process remains silent and unseen to ordinary sight. It is the transport stage of the auroral event, where the storm's released energy is carried inward along invisible lines toward the polar sky. Around each magnetic pole, the incoming particle streams do not spread across the whole hemisphere in an even blanket. They gather instead into a broad ring-shaped zone, and this zone is known as the auroral oval. The word oval is useful because the region is not a perfect circle drawn neatly around the geographic pole. It is an irregular, shifting band organized around the magnetic pole, shaped by Earth's magnetic geometry and by the changing state of the magnetosphere. In quieter conditions, this band remains confined to higher latitudes. During disturbed conditions, especially when a solar storm drives stronger energy transfer into the magnetosphere, the oval brightens, thickens, and expands farther from the pole. This expansion is one of the clearest large-scale signs that Earth's magnetic environment is responding strongly to solar forcing. Before individual colors or curtains are considered, the first visible change in where auroral activity appears is often this widening of the oval itself. The auroral oval exists because the magnetic field lines threading the upper atmosphere at high latitude connect to specific regions of the magnetosphere above. Some connect to the plasma sheet and inner magnetosphere, where disturbed particles and currents are organized during geomagnetic activity. Some map toward regions influenced by open magnetic flux and the broader polar cap. The oval therefore marks a transition region in magnetic geography. It is not merely a place in the atmosphere. It is the atmospheric footprint of larger structures in near-Earth space. What appears on the sky above the polar regions reflects which field lines are carrying energetic particles downward, how the magnetosphere is circulating plasma, and how much open magnetic flux has been created during storm conditions. The shape on the sky is therefore an echo of invisible magnetic structure far above it. In quiet times, the oval remains relatively narrow and tends to stay closer to the magnetic pole. It can still produce steady arcs and moving forms, but its average position remains limited to the usual high latitude zone. This is why auroras are more commonly seen from places nearer the poles, even when the sun is not especially disturbed. Earth's magnetosphere normally directs most of the relevant particle entry and current systems into those regions. During stronger solar wind driving, however, the magnetic system changes. More open magnetic flux is created on the day side and added to the magneto tail. The tail becomes more loaded, substorms become more likely, and the electric currents and particle precipitation associated with the auroral regions intensify. As this happens, the mapping between the magnetosphere and the upper atmosphere changes in scale. The region receiving auroral particle input extends farther from the pole. The oval expands. This expansion is not simply a matter of more light filling the same space, it is a change in magnetic footprint. When the polar cap grows because more open flux is present, the boundary between open and closed field regions shifts. The auroral oval, which lies near this broader transition between different magnetospheric domains, also shifts and broadens. In simple terms, stronger solar driving reorganizes the high-latitude magnetic map. The zone where field-aligned currents and energetic particle streams most strongly couple into the upper atmosphere moves outward. This is why storms can make auroras visible from latitudes much farther from the poles than usual. The change is not caused by the atmosphere alone. It is rooted in the geometry and loading of the magnetosphere. The oval is also not uniform around its entire circumference. Even when it is drawn in broad sketches as a ring around the pole, real auroral activity is stronger in some local time sectors than in others. On the night side, where substorm activity releases stored magnetotail energy, the auroral zone can become especially active and can surge equatorward more abruptly. On the dawn and dusk sides, different current systems and plasma populations influence the character of the oval. On the day side, precipitation can occur as well, though it often has a different structure from the more dramatic night-side expansions associated with substorms. This means the auroral oval is a living magnetic zone rather than a fixed border. Its position, width, and intensity vary around the pole and change with time as the magnetosphere continues to respond to solar forcing. Storm time expansion also gives the oval a more dynamic character from minute to minute. It may not move smoothly outward like an inflating ring. Instead, it can bulge, brighten, split into multiple arcs, and advance unevenly in different sectors. The night side portion may broaden rapidly during substorm expansion. The broader storm time oval can then remain extended for longer intervals if geomagnetic activity stays strong. In this way, the auroral oval reflects both the shorter pulse of substorms and the longer pressure of the wider geomagnetic storm. It is a boundary region shaped by both sudden release and sustained driving. That is why it can appear restless even when viewed only at the larger scale. The expansion of the oval also changes human experience of auroras. When geomagnetic conditions remain modest, the display is usually restricted to high-latitude observers. When the oval moves outward, many more regions fall beneath its reach. Places that rarely sit under the usual auroral zone can suddenly lie near its expanded edge. This does not mean the aurora has travelled across the whole planet in an undifferentiated way. It means the zone of high-latitude magnetic connection has widened enough to bring the atmospheric footprint of magnetospheric activity to lower magnetic latitudes. The distinction matters because the storm is not painting the sky at random. It is enlarging a structured ring of connection between space and atmosphere. There is also a vertical sense hidden inside this horizontal geography. The oval seen from below is a projection of magnetic field-aligned processes arriving from above. From the ground, it can seem like a band laid across the horizon or overhead. In physical terms, it is the lower visible expression of a three-dimensional magnetic funneling process. Countless field lines converge toward the polar upper atmosphere, and the oval marks where enough of those lines are carrying energy and particles to create a persistent zone of auroral activity. The expansion of the oval therefore means that the magnetosphere is engaging a larger portion of the upper atmosphere around the pole. Not that a thin line on the sky has simply been moved by wind. So this region of the story belongs to the widening polar footprint of the storm. The particles have already been guided down the magnetic field in organized streams. Now their entry zone around each pole grows broader and more active. The auroral oval expands, shifts, and thickens as Earth's magnetic system loads, releases, and reorganizes under solar driving. It is the large-scale map of where the storm is beginning to meet the upper atmosphere. The light itself is still not the main subject here. The subject is the ring-shaped region that suddenly spreads farther from the poles when the magnetic storm becomes strong enough. Above the denser weather layers of Earth, the atmosphere becomes thin enough that ordinary ideas of sky and air begin to lose their familiar meaning. In the high-latitude upper atmosphere, where the descending particle streams finally arrive, the gas is still present but spread far apart compared with the air near the surface. This region includes much of the thermosphere and the ionosphere, the part of the upper atmosphere in which many atoms and molecules are ionized and where electric and magnetic effects become especially important. It is here that the storm's long magnetic journey finally meets ordinary matter in a direct and repeated way. Until this point, the event has been a story of magnetic fields, plasma transport, current systems, and invisible acceleration. In this region, that invisible energy begins to enter the neutral upper atmosphere itself. The atmosphere does not stop the incoming electrons all at once. Instead, it receives them through countless collisions with atoms and molecules spread through a very large vertical range. NASA, NOAA, and ESA all describe auroras as beginning when energetic particles, especially electrons, collide with oxygen and nitrogen in the upper atmosphere. The upper atmosphere is thin enough that an incoming electron can travel some distance between collisions, yet thick enough that repeated collisions eventually become unavoidable. This balance is essential. If the air were much denser at these heights, the incoming particles would lose their energy too abruptly, and the large, delicate structure of the aurora would not develop in the same way. If the air were much thinner, too few collisions would occur to produce much visible light. In the actual upper atmosphere, the particle stream enters a region where the mean spacing between atmospheric particles still allows swift motion, but where enough oxygen and nitrogen remain to receive the storm's energy. The incoming electrons spiral and descend along magnetic field lines, and as they penetrate deeper into the high atmosphere, they begin to strike neutral atoms and molecules. Each collision transfers part of the electron's energy to the atmospheric target. Sometimes the collision excites the atom or molecule, meaning it lifts one of its electrons or internal energy states into a higher condition without removing it completely. Sometimes the collision ionizes the target, knocking an electron free and leaving the atom or molecule charged. Sometimes the collision mainly changes the motion of the particles, turning directed incoming energy into heat and random movement. The upper atmosphere is therefore not simply illuminated by the arrival of particles. It is physically altered by them, energized. ionized, and disturbed at the microscopic level. NOAA and NASA describe these impacts as collisions in the upper atmosphere that excite and ionize atmospheric particles. The most important immediate step for visible auroral light is excitation. An excited atom or molecule is not stable in that raised condition. It holds extra energy only briefly before returning toward a lower energy state. When it relaxes, it releases the excess energy as a photon, a particle of light. This is the basic mechanism by which the invisible descent of charged particles becomes a visible glow. The atmosphere does not shine because it has been heated until it glows like metal in a furnace. It shines because individual atoms and molecules are being driven into excited states and then releasing their excess energy in distinct emissions as they relax. This is why auroral light can be so clear, structured, and efficient even in very thin air. The process is more like electrical excitation in a gas discharge than like ordinary warming of a bulk material. NASA and NOAA both use this same essential explanation, comparing the aurora to gases glowing after energetic electrons excite them. Altitude matters greatly in this collision region. Higher in the atmosphere, the air is thinner, so incoming particles can travel longer before striking a target. Lower down, collisions become more frequent, and the incoming electrons lose their energy more quickly. Because of this, the depth reached by a particle depends on its energy. More energetic electrons can penetrate farther downward before being slowed significantly, while lower energy populations deposit more of their energy higher up. ESA notes that auroral electrons are stopped by collisions with neutral atoms and molecules across a broad range from a few hundred kilometers down to about 80 kilometers. This gives the aurora a vertical structure as well as a horizontal one. Different altitudes receive different levels of particle energy, different collision rates, and different balances between excitation, ionization, and heating. The visible aurora therefore occupies a layered atmospheric region rather than a flat shell. It is an interaction volume extending through the thin polar upper atmosphere, shaped by both the properties of the incoming particles and the density profile of the air through which they descend. The composition of the upper atmosphere also matters. At these heights, oxygen atoms and nitrogen in molecular and atomic forms are the principal participants in auroral collisions. They do not all respond in exactly the same way, and they do not all emit light on the same timescales or at the same characteristic wavelengths. What matters in this section is that the upper atmosphere is not chemically uniform in its behavior. It offers several kinds of targets to the incoming particle stream, and each kind stores and releases energy according to its own structure. Some excited states persist longer before emitting light, some relax more quickly. In denser parts of the upper atmosphere, an excited particle may collide again before it can emit a photon, a process that can suppress certain emissions and favor others. In thinner regions, radiative release is more likely to occur before another collision interrupts it. This means that the aurora's visible output is controlled not only by what arrives from space, but also by how the local atmosphere receives and processes that arrival. The upper atmosphere is not a passive screen. It is an active participant whose density and composition shape the final light-producing efficiency of the collisions. NASA and ESA both identify oxygen and nitrogen as the main atmospheric gases involved in the auroral process. There is also no single collision that creates the display by itself. The aurora is a collective effect built from immense numbers of tiny interactions. A single incoming electron can undergo many collisions before losing most of its energy. Each atmospheric atom or molecule can be excited, ionized, or left unchanged depending on the exact energy and geometry of the encounter. Across the polar upper atmosphere, sheets and streams of particles descend along magnetic pathways and produce vast populations of such microscopic events. From the ground, the observer sees a broad shining form. In physical reality, that form is being assembled moment by moment from innumerable exchanges of energy between charged particles from space and the rarefied gases of Earth's upper air. The scale is both grand and minute at once. The storm reaches across millions of kilometers from the Sun, yet its visible outcome depends on atomic and molecular collisions in air so thin that the sky remains almost transparent. So this region of the story belongs to the first true meeting between the storm and the atmosphere. The magnetosphere has guided the particles to high latitude. The auroral oval has marked the zone of entry. Now the descending electrons strike the thin upper air and transfer their energy into oxygen and nitrogen through excitation, ionization, and heating. Excited atmospheric particles then release photons as they return toward lower energy states. In this way, invisible magnetic disturbance becomes visible atmospheric light. The aurora begins here, in collisions within the high, thin, polar atmosphere where space weather finally becomes sky. Within the thin upper atmosphere, oxygen becomes one of the most important sources of auroral light. It is not oxygen in the familiar earthly sense of a gas being breathed near the surface. At auroral heights, much of the oxygen is present as single atoms rather than the paired molecules common in lower air. These atoms drift far apart in a rarefied environment shaped by altitude, sunlight, and the constant exchange between atmosphere and space. When energetic electrons descend into this region during an auroral event, atomic oxygen receives part of their energy through collisions. That transferred energy can lift the oxygen atom into an excited state. An excited state is a condition in which the atom holds more energy than usual and cannot remain there indefinitely. After a short or sometimes surprisingly long interval, the atom returns toward a lower energy state and releases the difference as light. In the aurora, oxygen produces some of the most recognizable emissions of all, especially green and red. These colors do not arise because oxygen itself is naturally green or red. They arise because oxygen atoms release energy in particular ways when they have been excited by incoming particles. Green is the most familiar auroral color because the oxygen emission responsible for it often forms strongly in the middle part of the auroral height range, where collisions and radiative release are balanced in a favorable way. In this region, the upper atmosphere is thin enough that excited oxygen atoms can often survive long enough to emit light, yet dense enough that substantial numbers of incoming electrons still deposit energy there. The result is a bright green glow that commonly dominates the visible display. From the ground, this green can appear as a soft arc, a bright curtain, a folded band, or a diffuse glow spread across a large part of the sky. Its prevalence gives many auroral displays their characteristic appearance. When people imagine an aurora, they often imagine this oxygen green first. The color has enough brightness and enough frequency of occurrence to become the visual signature of many geomagnetic disturbances. This green light is not produced instantly at the point of impact in the way a spark might appear from a struck surface. The incoming electrons excite oxygen atoms across a large volume of the upper atmosphere, and those atoms then release photons as they relax. The process remains microscopic in each individual atom, but the total effect becomes macroscopic because vast numbers of atoms are being excited over a broad altitude range. The green emission is especially efficient because the relevant oxygen transition can occur often enough under these conditions to build a bright collective glow. It does not require the atmosphere to become dense or hot in any ordinary sense. It only requires a region where atomic oxygen is abundant enough. the incoming electron energy is sufficient, and the collision environment allows the excited state to radiate before being interrupted too often by further collisions. Altitude is central to this balance. If the same oxygen excitation occurs too low in the atmosphere, where the air is denser, the excited oxygen atom is more likely to collide with another particle before it can emit its photon. In that case, the stored energy can be lost through collision rather than light. This suppression is often called collisional quenching. The word quenching here means that the atmosphere can deactivate the excited state before it shines. In denser air, this happens more readily. In thinner air, the atom has a better chance to radiate. The green oxygen emission therefore favours an atmospheric region where there is still enough oxygen to matter, but not so much surrounding density that the excited state is easily interrupted. This is one reason auroral colour depends so strongly on height. The atmosphere does not merely host the light, its density profile decides which excited states are allowed to shine efficiently. Red oxygen emission belongs to a different part of this same story. It also comes from atomic oxygen, but from a different excited state, with a different radiative timescale and a different sensitivity to the surrounding atmosphere. This red light is often softer, fainter, and more diffuse than the common green. It tends to form at higher altitudes where the atmosphere is even thinner. There, excited oxygen atoms can remain undisturbed for longer intervals before releasing their photons. Because the relevant red-producing state lasts longer than the green-producing one, it is more easily quenched in denser air, higher up, where collisions are less frequent. The red emission has a better chance to survive and appear. This is why red aurora often occupies the upper portion of a display or forms a faint crimson wash above brighter lower structures. It belongs to a thinner and calmer part of the collision environment. The red emission is often less obvious to the eye because it can be dimmer and more spread out. Human vision is not equally sensitive to all colours under dark conditions, and broad faint red glows may escape casual notice more easily than bright green forms. Yet during strong geomagnetic activity, red oxygen can become much more prominent. If the upper atmosphere at great height receives sustained excitation from incoming particles, the long-lived red-emitting oxygen state can build a visible luminous region extending above the brighter green layers. In some storms, this creates a striking vertical colour separation, with green below and red above, though the transition is rarely a hard boundary. The atmosphere is layered continuously, and the particle energies vary, so the colours often blend gradually through height, rather than stacking like solid bands. The timescales of these oxygen emissions also help shape the visual texture of the aurora. Green oxygen emission can respond relatively quickly enough to preserve some of the sharper folds and moving edges in an active display. Red oxygen emission, because of its longer lifetime, often appears smoother and less sharply structured. A rapidly changing particle input can therefore produce a more immediate green response, while the red component remains broader and softer, as if the upper atmosphere is averaging the disturbance over a longer interval. This difference does not mean the red layer is passive. It means the radiative physics of oxygen at those altitudes naturally favours a gentler visual form. The same storm can therefore create both active bright green curtains and a calmer red canopy through the differing behaviour of oxygen alone. Oxygen also helps reveal that auroral colour is not a decorative extra placed upon the physics. Colour is the physics made visible. Green and red do not merely beautify the sky, they show which atmospheric species is emitting, how high in the atmosphere the excitation occurs, how dense the surrounding air is, and how long the excited state survives before release. A green-dominated display points toward efficient oxygen emission at the more common middle auroral heights. A red-rich upper glow points toward thinner air, longer-lived excitation, and substantial energy deposition high above the denser layers below. In this way, oxygen turns the invisible structure of the upper atmosphere into something that can be seen directly from the ground. So this region of the story remains entirely within oxygen and its light. The incoming storm-driven electrons have already entered the upper atmosphere and begun colliding with atmospheric particles. Now, the specific behavior of atomic oxygen shapes the aurora's most familiar colors. Green appears where oxygen can radiate efficiently in the denser part of the upper auroral zone. Red appears higher, where thinner air allows longer-lived excited oxygen to shine before collisions silence it. The result is a sky in which one atmospheric element, energized by space weather, reveals altitude, density, and atomic timescale through color alone. Nitrogen adds a different set of tones to the aurora, and with it the display becomes more varied in both color and texture, where oxygen often provides the broad green glow and the higher soft red light. Nitrogen contributes cooler and often sharper colors, including blue, violet, purple, and pink. These colors do not come from one single form of nitrogen acting in one single way. In the upper atmosphere, nitrogen can appear as molecular nitrogen, which consists of two nitrogen atoms bound together, and as ionized molecular nitrogen, in which that molecule has lost an electron and carries electric charge. Both forms can participate in auroral emission. When descending electrons from the magnetosphere collide with nitrogen, they can excite it into higher energy states, just as they do with oxygen. As those excited states relax, nitrogen releases photons at characteristic wavelengths. The result is a family of colors that differ from oxygen not only in hue, but also in where they appear, how quickly they are emitted, and how they shape the visible structure of the aurora. The most important contrast begins with altitude. Nitrogen emissions often become especially significant at somewhat lower auroral heights than the highest red oxygen glow. This does not mean they are confined to a single narrow layer, because the auroral collision region remains broad and vertically extended. Still, nitrogen commonly contributes more strongly where the atmosphere is denser than the very high levels that favor the long-lived red oxygen state. In these somewhat lower regions, incoming electrons that retain enough energy continue downward and collide frequently with atmospheric molecules. Molecular nitrogen and ionized molecular nitrogen respond by producing blue and purple emissions, especially when the particle precipitation is energetic enough to penetrate more deeply into the upper atmosphere. This is why auroral displays with strong lower edges or more active lower fringes often show nitrogen colors along these regions. The distinction between neutral and ionized nitrogen matters because they do not emit in exactly the same way. Molecular nitrogen can produce bands of emission in the red and blue parts of the spectrum, while ionized molecular nitrogen is especially important for some of the blue and violet tones often associated with active aurora. In a natural display seen by the eye, these emissions often blend together rather than appearing as isolated pure colors. Blue can merge with red oxygen or red nitrogen contributions and create pink or magenta tones. Violet can mix visually with neighboring emissions and appear purple. The sky does not separate these processes into tidy single-color strips. The upper atmosphere presents a layered and blended optical result formed from many emissions occurring at once over different heights and intensities. Nitrogen light also tends to be associated with more energetic precipitation. Lower altitudes require incoming electrons with enough energy to keep traveling downward, before losing most of their motion to collisions above. When such electrons reach denser parts of the auroral zone, they can excite nitrogen efficiently. This links nitrogen-rich color to intervals or regions of stronger particle input. The presence of blue, purple, or bright pink lower edges can therefore indicate that a more energetic population of electrons is reaching deeper into the atmosphere. This does not mean every blue or pink feature marks an extreme event, but in general, nitrogen colours are more likely to become obvious when the incoming precipitation is sufficiently energetic and organised. The timescales of nitrogen emission are also important for the appearance of the aurora. Many nitrogen emissions occur on shorter timescales than the long-lived red oxygen state. Because of this, they can respond more promptly to rapid changes in incoming particle flux. A shifting or intensifying beam of electrons can produce nitrogen light that traces finer, faster changing structures, especially near the lower edges of curtains and along bright folds. This helps explain why blue or purple tones can appear near sharper borders or more active lower fringes of the aurora. In visual terms, nitrogen often contributes crispness where oxygen, especially high red oxygen, contributes softness. Density in the atmosphere plays a double role here. On one hand, nitrogen emissions often benefit from the somewhat denser lower part of the auroral region, because energetic electrons can deposit substantial energy there. On the other hand, if the atmosphere becomes too dense, collisional quenching can again suppress certain excited states before they radiate. This means the visible nitrogen layer also occupies a balance region, rather than extending indefinitely downward. The incoming particles lose energy as they descend, and the atmosphere becomes more collisionally effective at shutting down some emissions. So the strongest visible nitrogen contribution tends to belong to lower auroral altitudes, but still well above the dense lower atmosphere where the sky no longer behaves as a thin emitting medium. Blue and violet are often harder for the eye to detect clearly than green, especially when the display is faint. During active intervals, however, pink lower rims, violet fringes, and bluish highlights can become obvious. These colours often appear where the aurora is brighter, more structured, and more rapidly changing. In this way, nitrogen helps give the aurora its sense of liveliness and complexity, especially near lower borders and active folds where the particle input is intense enough to make those emissions stand out against the more widespread green background. Nitrogen therefore does not replace oxygen in the auroral display. It works beside it, adding another atmospheric voice to the light. Oxygen reveals broad middle and upper altitude structure through green and red. Nitrogen reveals lower and often more energetic structure through blue, violet, purple, and pink. The final visual result is a combined atmospheric response to incoming space weather energy. One species does not paint the sky alone. Multiple gases emit at once, and the eye receives their sum as a layered and shifting display. Nitrogen is responsible for much of what makes the aurora look richer than a single green glow. So this region of the story remains entirely within nitrogen and its emissions. The descending electrons have already entered the upper atmosphere and begun colliding with atmospheric particles. Here, molecular nitrogen and ionized molecular nitrogen receive that energy and return it as blue, violet, purple, and pink light. Their emissions favour somewhat lower parts of the auroral region, respond well to more energetic precipitation, and often track sharper and more active structures. In this way, nitrogen turns the lower and more energetic edges of the aurora into a visible record of how deeply and intensely the storm-driven particles are entering the upper atmosphere. The aurora, once fully visible in the night sky, appears less like a fixed object than like a changing architecture of light. What has travelled outward from the sun, crossed interplanetary space, entered Earth's magnetic environment, stored energy in the magnetotail, returned along polar field lines, and collided with the upper atmosphere now becomes a form that human sight can finally follow directly. Yet even at this final visible stage, the display is not still. It brightens, fades, bends, divides, ripples, and reforms because the light is being produced in a region where particle input, atmospheric response, and magnetic structure are all changing together. The visible aurora is therefore not a painted surface laid across the sky. It is the moving optical face of an active connection between space and atmosphere. When a solar storm intensifies that connection, the sky can seem to answer suddenly, not because the atmosphere itself chooses to move in this way, but because the invisible systems above it are feeding energy into the upper air with greater force and greater organization than before. One of the most common large forms is the arc. An auroral arc appears as a long curved band stretched across part of the sky, often narrow at first and sharply defined along one edge. This shape reflects the way particle precipitation and electric current are organized along extended magnetic boundaries rather than scattered at random. The arc can remain quiet and steady for a time, giving the impression of calm structure suspended over the polar region. Then, as the incoming particle flow changes, the arc can intensify, its edge brightens, its width increases. Fine folds begin to hang downward from it. What was once a simple band becomes a curtain. The word curtain is useful because the aurora often appears as a vertically folded sheet, with bright drapery-like pleats created by the perspective of looking through long-aligned structures in the upper atmosphere. These folds are not fabric, but narrow luminous regions traced out by magnetic organization and atmospheric emission over great height. The eye reads them as hanging forms because the emitting region extends upward through a tall volume of thin air. Motion enters the display because the source regions of the particle streams are changing, and because electric fields in the ionosphere and magnetosphere move the pattern across the sky. An auroral curtain can drift sideways, spread, contract, or suddenly become lined with rapidly moving rays. Rays are narrow, bright streaks that often appear to point upward from the arc or curtain. Their apparent verticality is shaped partly by magnetic geometry, since the particle precipitation follows field-aligned paths, and partly by perspective, since an observer on the ground looks along and across a three-dimensional volume of light. When many rays brighten together, the sky can seem ribbed or combed with luminous lines. These lines can flicker and reorganize rapidly, not because the whole atmosphere is shaking, but because the pattern of incoming electrons and the local electric currents are changing on short timescales. The faster the particle input varies, and the more sharply structured the precipitation becomes, the more alive the aurora appears. A storm makes the aurora suddenly surge because it increases both the amount of energy entering the upper atmosphere and the area over which that energy is being delivered. The auroral oval expands to lower magnetic latitudes, so more sky becomes involved. At the same time, stronger particle precipitation raises the emission rate in the upper atmosphere, so regions that had been faint can become bright enough to stand out clearly. The night-side response to substorm activity is especially important in producing abrupt brightening. A relatively quiet arc can suddenly intensify, bulge, and race across the sky as magnetotail energy is released and routed into the polar ionosphere. This is often called auroral breakup, though the term does not mean destruction. It means the earlier quiet form breaks into more active motion, spreading into brighter, more complex, and faster evolving structures. The calm arc becomes a dynamic field of folds, curls, and rays. The apparent flowing and rippling of the aurora also comes from the fact that the display is not one thin line but a layered emitting volume seen in perspective. Different parts of that volume can brighten at different moments and at different heights. One layer may emphasize oxygen green, another oxygen red, another nitrogen pink or violet along lower active edges. As these emissions vary in intensity, and as the viewing angle changes across the sky, the display can appear to undulate like a living surface. Yet the motion is not wind-driven in the ordinary atmospheric sense. It is controlled by changing particle precipitation, field-aligned current systems, and the electrodynamic response of the high-latitude ionosphere. The upper atmosphere glows where energy is being deposited, and because that deposition shifts across space and time, the luminous forms seem to flow. Brightness itself can change very quickly. A faint band can become vivid within moments if the incoming particle flux increases. A broad glow can sharpen into a defined arc when the precipitation becomes more structured. A stable curtain can fragment into multiple parallel forms if neighboring magnetic channels begin carrying different intensities of current and particle input. The aurora is therefore not only an emission phenomenon, but a mapping phenomenon. It maps the changing state of near-Earth space into visible patterns above the poles. A surge in the sky is the visible signature of a surge in magnetospheric coupling. A widening, luminous band is the visible footprint of an expanded auroral oval. A rapidly brightening curtain is the atmospheric expression of reorganized particle streams descending through magnetic funnels. Color deepens the sense of movement because different emissions dominate different parts of the display. Green often fills the main body of bright curtains. Red may hover above as a more diffuse canopy, especially during stronger activity. Pink and purple can trace lower fringes and sharper active edges where more energetic electrons penetrate deeper into the atmosphere. When all of these emissions overlap within one evolving volume, the aurora can appear layered and textured rather than flat. The brighter the storm-driven precipitation, the more dramatic these relationships can become. Yet even in its most active state, the aurora remains a precise natural response to atomic and molecular excitation in thin air, not a mystical or arbitrary light. Its beauty comes directly from the discipline of the underlying physics. So this final region of the subject rests entirely in the visible sky. The solar storm has already done its work across the Sun, the heliosphere, the magnetosphere, and the upper atmosphere. What remains is the final appearance of that work as seen from below, arcs that brighten, curtains that fold, rays that shimmer, and an auroral oval that spreads farther from the pole when geomagnetic driving grows strong. The sudden surge of auroras is therefore not sudden in origin. It is the last visible step in a long chain of solar, magnetic, and atmospheric processes. By the time the night sky ripples with light, the storm has already crossed millions of kilometers and passed through many invisible regions before finally becoming color in the polar air. The sky grows quieter once the strongest surges pass. The brighter folds soften into broader light, and the sharper edges lose some of their force. What remains is still the same aurora, but now it seems less like a sudden response and more like a long exchange gradually easing. High above the planet, the upper atmosphere continues to release the energy it has received. Oxygen still glows in green and sometimes red. Nitrogen still adds faint traces of cooler color. Yet the motion becomes gentler. The sky no longer seems to open all at once. It settles into slower bands, dimmer curtains, and wider spaces of darkness between them. Far beyond sight, the magnetosphere also begins to relax. The tail releases less tension. The flow of particles along magnetic field lines becomes less intense. The oval around each pole narrows again toward its quieter form. None of this happens in a single instant. The storm does not stop as though a switch has been turned. It eases through layers. First, the visible sky becomes less active. Then the upper atmosphere receives less incoming energy. then the larger magnetic system gives back more of its stretched shape. What appears calm at the end is not a return to stillness without history. It is the result of a chain of forces slowly losing intensity. In that fading light, the aurora reveals its full nature most clearly. It is not only colour in the night, it is the visible edge of a connection that begins at the sun, travels across open space, enters Earth's magnetic field, and finally touches the thinnest air above the poles. When the glow weakens, that long connection becomes harder to see, but it does not become less real. It simply withdraws again into the invisible regions from which it came, leaving the sky dark, the atmosphere quiet, and the planet once more under a calmer magnetic night.